So this section is called Electrostatics. And just like the name sounds, it's about charged particles that are stationary, essentially. There are two types of charged particles. A positive. This is what we'll encounter as a positive charge is typically the proton, and negative the electron. And these are the two we'll encounter. These are the ones that we see most often in physics and chemistry, at least at this level. But there's also another particle in the atom, so atoms have protons, neutrons, and electrons. Right, these two guys live in the nucleus, and this guy orbits the nucleus somehow. Right, most of the mass of an atom is in the protons and the neutrons, and most of the volume of an atom is in the space that the electrons live in. A typical example is if you had a football, if you blew the atom up to the size of a football stadium, so this is a football stadium. The nucleus would be the size of a pencil eraser or something like that in the center. So most of the volume is in the electrons. But the mass is in the nucleus. So the charge on the charge, a proton has charge 1.6 times 10 to the minus 19th coulombs, and actually this defines a coulomb because we can say so typically we're moving lots of charges when we have a current or something like that, or the charge on something, and so we don't want to use proton charges, so we want to use some large number of charges in the same way that we don't want to measure large distances in inches or millimeters. And so this many protons is a coulomb. And so if you invert that, you get this number, and so one proton has this many coulombs of charge. We give the quantity E, the charge on 1.6 times 10 to the minus 19th coulombs. That's the charge on either an electron or a proton. Notice it's positive in the same way, G equals 9.8 meters per second is positive. And so the charge on an electron is minus E. So we can also say, for example, the mass of a proton, which sometimes comes up, is about 1.67 times 10 to the minus 27 kilograms, which is approximately equal to the mass of a neutron. And then the mass of an electron is 9.11 times 10 to the minus 31 kilograms. So the ratio of those two is about 1800. So the mass of a proton is about 1800 times the mass on an electron. And so that just says that since a neutral atom has equal numbers of protons and electrons, that just says that the nucleus is at least 1800 times more massive than than all the electrons in the atom. And it's more than that because there are neutrons that haven't been counted here. So that's why we say all the mass is in the nucleus. So if we want to talk about charges and how they act on each other, right? Hang on one second. So it turns out there's a law for the force of for the electrical force between charged particles, and it's been attributed to a French gentleman named Charles Coulomb, but he was not the first. But we call it the Coulomb force. If this formula looks familiar, it's because it should. It looks a lot like the gravitational force. Right, that Isaac Newton came up for the force of gravity. It's no accident that when physicists and chemists were looking for the interaction force between charged particles, that they thought, well, maybe it's got a similar form to the one for gravity, and so they tried this, and it works. This constant, if you remember, the G constant was 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. The Coulomb constant K is 9 times 10 to the 9th Newton meter squared per Coulomb squared. Notice that this quantity on the right-hand side has to come out in newtons because this is a force, and forces are in newtons. And that means that when you multiply whatever this guy's units are by Coulomb squared over meter squared, you have to get newtons. And so that's how we know it's newtons times meter squared over Coulomb squared. So these two guys cancel out, and I'm left with newtons. A couple of other things to notice about this. When F is less than 0, is attractive. The force is attractive, right? Because we said opposite signs attract. So if they're opposite, that means one is positive and one is negative. Doesn't matter which. Then this is a negative sign. And so negative on this evaluation of this force means an attractive force. F greater than 0 is repulsive. That means if they're both negative, right, then the result is positive, or if they're both positive, then the result is positive. Notice D squared can never be negative because it's squared, and K is a positive constant. So we can use this to evaluate some forces. And so we can say, for example, let me just stop there for a minute. So now we can ask the question, what is the force between an electron and a proton and a hydrogen atom, where the distance between them is on average about 10 to the minus 10 meters. So, here's my hydrogen atom and here's the electron orbiting around it. A hydrogen atom just has a proton in the middle and an electron going around, and this is this sort of planetary picture, which is obviously wrong. But we can calculate the average distance, and it's about 10 to the minus 10 meters. And so we can say, look, the force between the proton and the electron is K q proton times q electron over the distance between them squared. This, by the way, is why you often see an R here, because this is the distance, right? And it's often the radius of a circle or something like that. But it's just the distance between the two particles. You can call it a radius, or you can call it the distance, or you can call it anything you want. And so we can just evaluate this thing. It's 9 times 10 to the 9th Newton meter squared per Coulomb squared times charge on a proton, which is 1.6 times 10 to the minus 19th coulombs, times the charge on an electron, which is minus 1.6 times 10 to the minus 19th coulombs, divided by 10 to the minus 10 meters squared. And so when we evaluate that, we get, and I'll have to look that up real quick, negative 2.3 times 10 to the minus 8 newtons. And so that's, 2.3 hundred millionths of a newton, and the force is attractive. Often we know, if we know the sign of the charges, we know the force is either attractive or repulsive, and we know which it is typically. And so often we're just looking for the magnitude of this. But anyway, that's the force. And we don't have anything to compare it to, so that's the force. But then we could say, instead of looking at the force between the charges, we'll look at the gravitational force between them, because we know that the formula for the gravitational force is what we covered last semester. And we can say, look, the gravitational force is just g times the mass of the proton times the mass of the electron over the distance squared. So it's the same distance, and now we have 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared times the mass of a proton, which we said in the previous video is 1.67 times 10 to the negative 27 kilograms times the mass of an electron, which is 9.11 times 10 to the negative 31 kilograms, all that over 10 to the minus 10 meters squared. And this comes out to be about 1.0 times 10 to the minus 47 newtons. And so if you remember just a minute ago, we said the electrical force was minus 2.3 times 10 to the minus 8th. And so when you contrast these two, this is a decimal point, 46 zeros and a 1. This is a decimal point, 7 zeros and a 2. So I would have to keep an additional approximately 40 digits in this number for this one to start to matter. So typically, the force of gravity is much, much less than the Coulomb force, unless the objects are very large and neutral, like planets or something like that. But when we look at charged particles, this one is almost always irrelevant, and it's why you never talk about gravitational attraction in your chemistry class. So in this problem, we say how many kilograms of electrons when you need on Earth and the Moon, assume equal amounts, to steal the Moon. In other words, here's the Earth, right, and here's the Moon. And we know that these two attract, right? Earth and Moon. And so the force of gravity between them is g times the mass of the Earth times the mass of the Moon over the distance between them squared. And that's 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared times the mass of the Earth, which is 6 times 10 to the 24th kilograms, times the mass of the Moon, which is 7.35 times 10 to the 22nd kilograms. Notice you can see in this equation that the Moon is about 1/100th the mass of the Earth, a little more. But it's less than 2% the mass of the Earth. Even though it's a quarter the diameter, it's less than 2% of the mass. Divided by the distance between them squared, which is 3.84 times 10 to the 8th meters squared. If you evaluate this number, what you get is the force of gravity is equal to about 2 times 10 to the 20th newtons. And so what we want to do is we want to say, look, let's produce a Coulomb force, which is K, Q Earth, Q Moon. These are the extra charges we put on the Earth and the Moon over the distance squared, same distance, so that this force is equal to that force. In other words, we've just put enough repulsive force on each of these guys to get them out, where we've added the additional requirement that the charge on the Earth is just the same as the charge on the Moon, which we'll just call Q. And so then we can say the Coulomb force is just K Q squared over D squared. And this is equal to, we want it just equal to that, right? 2 times 10 to the 20th newtons. And so we know D, we know K, we're going to solve for Q. Q, if I just look at this equation, right? I'll say Q squared. Q squared is equal to the Coulomb force times D squared over K, or Q is equal to the square root of the Coulomb force required times the square of the distance between them divided by the Coulomb constant. And this is equal to the square root of 2 times 10 to the 20th newtons times 3.84 times 10 to the 8th meters squared over 9 times 10 to the 9th Newton meter squared over Coulomb squared. Make sure my radical goes all the way down. And what I get for this is about 5.7 times 10 to the 13th coulombs. So that's the charge, right? That's the charge that gets me a force that equals the gravitational force, but instead of being attractive like gravity, it's repulsive. And so if I can put this many charges on the Earth and the Moon, then I can free the Moon. However, there's a catch to this. This problem asked me for how many kilograms, and this is coulombs, right? And so I know that if I want my charge in electrons, I can say Q equals 5.7 times 10 to the 13th coulombs times 1 coulomb over I want to convert this into electrons, and so I'm going to say 6.25 times 10 to the 18th electrons per coulomb. Right, this was this number that showed, right, I'm doing a unit conversion, so this piece is equal to 1. Let me write it again so it's just a little bit clearer, right? 6.25 times 10 to the 18th electrons per coulomb. Now my coulombs cancel, and this gives me a number that's like 3.6 times 10 to the 32nd electrons. So that's how many charges I need. I should technically have a minus sign here, but I'm just interested in how many charges are required. And so that's how many electrons I need, or protons, but we're going to use electrons because they have a lower mass, right? And so now I can say the mass is just equal to 3.6 times 10 to the 32nd electrons times 9.11 times 10 to the minus 31 kilograms per electron. This is also equal to 1, and I'm just doing a unit conversion to mass, and this gives me about 330 kilograms. So 330 kilograms of electrons, if you were to steal 330 kilograms of electrons somewhere, that's less than 1,000 pounds. So it's less than the weight of a car, right, in electrons. You can almost fit it in a suitcase, except that they repel each other really bad and wouldn't stay inside the suitcase. But this many electrons, so if you're an evil villain, if you're a James Bond villain, come up with a device that will allow you to steal the moon by putting that many kilograms on each of the Earth and the moon, and you can ride the moon off into space.